The shower video from part 1 introduced us to a constant rate of flow. Watch the following short video, which presents a different flow situation. Your task is to contrast this situation with that seen in the shower video. As you watch this situation, list on paper things you notice that are different between the two situations.
Yeah, that's going to work. Beautiful. Nothing uneven.
So what made your list of differences? Did you include the different coloured water, the outdoor setting, the naughty dog's reflection in the window? Well, while all those are valid, I hope you also noticed something about the water's rate of flow. Did the rate of flow seem different to the rate of flow in the shower? To me, it seems slower. It took way longer to fill the jug, well over 40 seconds. I could hear the rate was not constant. It seemed to me that the rate of flow was in fact getting slower or decreasing as each few seconds passed. The gurgling at the end, in particular, drew my attention to this. So it seems this situation introduces us to a decreasing rate of flow. Did you wonder how the decreasing rate of flow was created? Try to come up with at least 2 theories before I tell you how it was actually done. Gravity was the secret rate of flow decreaser. The weight of the head of water is continuously reducing, and as such, the rate of flow into the jug starts at some value and then continuously decreases. How would we measure such a rate of flow? A rate that continuously changes. Well, thinking about it, it seems sensible that we might be able to measure the rate of flow at an instant. Imagine we can freeze time, say at the 40-second instant. At that instant, the rate of flow would have some value. But of course, a moment later, it will be a little slower. I'll play the video again for you. Do your best to calculate how fast the water was flowing into the jug at the 40-second instant. I'll have a go too and share my effort with you in the next part of this video. Then you can compare your effort to mine.
Yeah, that's going to work. Beautiful. Nothing uneven.
How did you go? Before I show you my approach, I will show you two approaches from other people that I have seen before. Both approaches are based on data from the video, the time taken for each half litre to flow into the jug. Approach 1 starts by making a plot of volume versus time and finding the quadratic curve of best fit. In this case, V of t is equal to negative 0.0005 t squared plus 0.1 t plus 0.04, and then finding V of 40. But this calculates the volume in the jug at the 40-second instant, not the rate of flow or the speed at which the water is entering. So on its own, this is not so helpful. Approach 2 acknowledges that we might need to incorporate the gradient of a straight line somehow. As such, a plot of volume versus time is made, and the quadratic curve of best fit is found once again. For the remainder of this video, we will use V of t is equal to negative 0.0005 t squared plus 0.1 t, since we know that V of 0 is equal to 0. Next, a straight line is drawn through the origin and the point 40, 3.2. Then the gradient of this line is calculated, which in this case is 0.08. And so the conclusion is that the rate of flow is 0.08 litres per second. While this is not correct, it is a nice attempt. It actually calculates the constant rate of flow that would have delivered the same total volume of water in the initial 40-second interval that the continuously decreasing rate of flow delivered. The value calculated is called the average rate of flow over the given time period. Oh, by the way, a straight line cutting a curve like this one is given a fancy name. It's called a secant. It is interesting to note that the rate of flow at the 40-second instant, which we will call R of 40, would have to be less than the average of 0.08. Why? Well, if R of 40 was equal to 0.08, then R at any time prior to the 40-second instant would be greater than 0.08, as we know the rate was decreasing over time. Hence, the total amount of water delivered would have to be more than 3.2 litres. Similarly, the rate of flow at the 0-second instant, R of 0, would have to be larger than 0.08. So the average rate of flow lies in between the instantaneous rates R of 0 and R of 40.